Good morning, people. Who we got? One, two, three, four people. Hello, where's everybody? Oh, well, it's up to them, right? You are adults. You can decide if you come or not. Okay, so I thought I was going to have a short lecture today, but yesterday I had some time, so I extended the lecture to make it a little more complete, and I think it's going to be a little longer than that. I don't know how long it's going to be, but it's all about blood pressure. So let's go ahead and get started. Come on. Come on, baby. There we are, blood pressure. So the thing about long-term blood control of blood pressure, like we talked previously about autonomic control of blood pressure, and all that hemodynamic stuff was about how changing different autonomic nervous things changes the blood pressure, which is all kind of really minute to minute, second to second, hour to hour changes, really minute to minute, second to second, really. So a lot of that comes into play when you're laying down, you get up. That's postural changes. Comes into play whenever your activity changes. Whenever you go from sitting to standing, then you go from walking to running. Any kind of change in your activity is going to be responded to quickly by your ANS. In fact, when you inhale, you put more pressure in your thoracic cavity, and that hits the baroreceptors, and your heart slows down. When you exhale, the pressure decreases in your thoracic cavity, and that hits the baroreceptors, and your heartbeat slows up or it speeds up. So everything happens really, really fast, and it's really tightly controlled. But long-term control is not about your autonomic nervous system, although we can affect blood pressure by intervening in the autonomic nervous system. Long-term control is about blood volume because it's a closed system. You put more water in the balloon, the tension in the wall gets tighter, and that's your long-term blood pressure control. And as we all know, blood volume is controlled by the kidneys. So we're going to start out talking about the kidneys. So ANS is responsible for critical minute-to-minute control of blood pressure, second to second, microsecond to microsecond. It's very, very well attuned. Long-term control is by blood volume because this cardiovascular system is a closed loop. Putting more blood in increases the blood pressure. And when we talk about putting more blood in, we're talking about putting more water in, which means putting more sodium in. It's all about sodium control. Here is your kidney or my kidney. And there are two main sections. Well, there are a lot of sections here, but the thing we care most about is the outside is the cortex. And that's just a general term for the outside of anything, like your adrenal cortex and your adrenal medulla. So the kidney then has a cortex and it's got a medulla. And that's important because part of the nephron will be out here in the cortex and part of it will be in the medulla. So the nephron is our functional unit of the kidney. And we'll be looking into all the sections of the nephron today. Once the nephron gets done with its processing, it makes urine. The urine goes down the collecting ducts and then out through the ureters. So here is the nephron. So structures you need to know in the nephron are the proximal tubule, okay? Well, wait, first, let's start here. So first is the glomerulus, which is the arterial part of it. Bowman's capsule then is the nephron part of it. And then there is the proximal convoluted tubule, proximal meaning close to the glomerulus. Then you've got the loop of Henle, and then you've got the distal convoluted tubule, and then you've got the collecting ducts. So the collecting ducts will all come together into the ureter. Ureter goes to the bladder, bladder goes to the urethra. So, and that's some serious anatomy coming from me because that's about all I know about anatomy. In addition to that, you've got these arteries here that do the reabsorption of stuff after, oh shit, I hate when that happens. Oh man, sorry. I've got a very sensitive touchpad here, and so my finger hovers over the touchpad, and suddenly it senses that as a hit, and then I go to that link, and I want to do that. Anyway, so anyway, the arteries then are reabsorbing stuff that the nephron is not going to keep. Let me see, what is the next one? Yeah, okay. So blood comes into the glomerulus through the afferent arteriole. And in here, you've got some very porous capillary. It's a capillary system. It's very, very porous. So it's like a filter, basically. And then your efferent arteriole comes out from there. Now, when all this fluid gets filtered out from the glomerulus, it gets picked up by the Bowman's capsule and then goes down into the proximal tubule. So this is called the glomerular fluid, and then once it gets down here, it's called the tubular fluid. This nitrate is, don't worry about that. That's from I stole this figure from somewhere. You can see where I stole it if you click into it. Okay, so glomerulus. Let's go from the top to the bottom. Glomerulus. Convoluted capillaries from the afferent arteriole, and they're very leaky. So basically anything smaller than a protein will leak into this. And that's something that's kind of interesting to me anyway, and that's why like your urine is sterile, right? Even if you've got a raging septic infection, bacteria are too big to come out into this glomerular filtrate. And there's no way for anything to get into that nephron or the collecting tubes once the fluid is in there. So the fluid is going to be totally sterile all the way down the ureters into your bladder and out your urethra. Unless you've got some kind of a UTI or bladder infection, urine is sterile. And in a lot of poorer countries, they'll use urine to clean out wounds, because it's sterile water. And I think that's mainly like very desert-like countries that don't have, and it's kind of like traditional. I don't know if people really do that today, but back in the day, back when I was young, no. Anyway, all right. So filtering out anything smaller than a protein. If you got protein in your urine, that's a problem. It's a symptom of a problem. So should be no proteins there. And then this leads to the efferent arteriole, which will then wrap around the loop of Henry. The efferent arteriole is narrower than the afferent arteriole, so you're kind of restricting the flow out, and that helps to filter more. It's easier for blood to come in than to go out, so that gives you a little bit of back pressure to filter. So about 20% of the plasma gets filtered out, and it's indiscriminate, right? It's not choosing anything, it's just dumping everything out. I'll be here. Dog. Okay, Bowman's capsule. So Bowman's capsule then collects the filtered plasma, and it's called the filtrate, and then directs that filtrate to the renal tube. So not a lot of functionality here. It just kind of grabs the fluid and gives it to the proximal, the renal tube, which is starting with the proximal convoluted tubule. So the renal tube then is going to reabsorb lost electrolytes and nutrients, concentrate the tubular fluid, and then send the urine into the collecting duct. So the renal tubule is doing most of the work here. The first thing we're going to come to is the proximal convoluted tubule, then the loop of Henle. You've got your descending loop and your ascending loop, and that's where we're going to get our counter current ion exchange. And then you've got your distal convoluted tubule and the connecting tubule. And we've got drugs that are going to affect different parts of this to give us our diuresis and decrease in blood pressure. Proximal tubule. And the function here is it's going to reabsorb a lot of that fluid that got filtered out and put it into those peritubular capillaries. We're reabsorbing salt and water here and glucose and amino acids. So if you've got some toxin, like this is all specific reabsorption. So it's not just you filter everything out, then you pull it all back in. We're only pulling back in what we know we want. So glucose, amino acids, salts, and water. So any toxins are going to stay in that proximal tubule. And here, since we've got a lot of absorption, we've got something similar to what we see in the intestines. We've got brush border cells, which on the apical surface that faces the lumen have got microvilli. Okay, with this background, my hand keeps disappearing. You've got microvilli to increase the surface area and get you the absorption you need there. Loop of Henle then, this is where a lot of the work happens, and this is your countercurrent exchange. So this is a really cool mechanism. I remember when I first learned about it, I thought, oh my God, this is the coolest thing in the world. And it is kind of, well, maybe not the coolest thing. I mean, there's still, Taylor Swift. I am a Swiftie, but it's very cool nonetheless. Descending limb, shake it off, shake it off. Descending limb is permeable to water, but not to salt, okay? So no salts are leaving, but water can leave depending on the osmolarity in the interstitial fluid around the descending limb. And it's descending from the cortex down into the medulla. And the osmotic strength is going to increase as you go down deeper into the medulla. So as you go down deeper into the medulla, water's coming out of that filtrate or the tubular fluid. So we're concentrating the fluid as we come down the descending limb. The ascending limb is then impermeable to water. Oh, go lay down. Come on, lay down. Impermeable to water. But we're actively secreting salt. So this is why you've got that osmotic pressure changing as you come down, because down at the bottom of that loop, you're excreting salt. And so that's putting a lot of salt out there and making it very hypertonic. And as you come up that tube towards the cortex, that fluid has got less and less sodium in it because you're actively secreting it out. And so when you get to the top, there's not a lot of salt left, and that gives you your gradient, bottom to top of sodium, and therefore osmolarity. And I'll show you a figure of that I think hopefully makes it a little more obvious. So as you're ascending the cortex, the tubule becomes more and more, I shouldn't say hypotonic, it's always isotonic, but it becomes a lower tonicity as you go up. And that produces your osmotic gradient. Okay, so here we are. Here's your dilute fluid coming into the tubule here. And here you are losing water because here's your osmolarity in that interstitial fluid. Starts at 300, which is normal, right? That's the osmolarity of blood. Down here, it's 1100, even 1200. So it gets more and more hypertonic as you go down. So as the fluid's coming down, water is equilibrating with this tonicity. So water is leaving, concentrating the salt. You turn the corner, and now you're actively excreting sodium and chloride. So that is producing this gradient here because you're excreting that sodium and chloride. And now once you get to the top of this limb, most of the sodium and chloride is gone. So now you're in a very hypotonic state. Now remember, this is impervious to water, so you can be hypotonic here without osmolarity trying to equalize here. So when you get here, you've gotten rid of a lot of the water, and then you've gotten rid of a lot of the salt, and so you end up hypotonic. So that is the urine at this point. So the loop of Henle, the distal convoluted tubule. Why does it say loop of Henle? Shouldn't say that. Hang on. Bum, 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 bum. Here we go. Seeing behind the curtain again, people. You're so lucky. See how the sausage is made. Okay. The distal convoluted tubule then, loop of Henle dumps into the distal convoluted tubule. What the hell has happened? And here you get active reabsorption of sodium and calcium. And this is important because this is where some hormones are going to act, and we can interdict hormones with drugs if we want to. So both sodium and calcium are under endocrine control. So aldosterone is affecting the sodium reabsorption here, and parathyroid hormone is affecting the calcium reabsorption. So parathyroid is the hormone, or the organ, by releasing the hormone that controls your calcium level. It both increases reabsorption of calcium here and increases resorption of calcium from your bones. So it's really important to keep calcium level right. Remember how important calcium is to just about every signal transduction mechanism. So that extracellular concentration of calcium has to be really, really well established. Okay, once we pass our distal convoluted tubule, we get into the collecting ducts. So the collecting ducts then are impermeable to water normally, okay? They can be made permeable by putting up aquaporins. So this is like almost like axon bulb, in the axon bulb, where you've got subcellular subsurface vesicles with these aquaporins in them. And when antidiuretic hormone comes along, it goes up into the it puts these aquaporins into the membrane, and then that causes water reabsorption. Okay, so that's important. We'll talk about that again today. ADH then is a hormone that causes water reabsorption, increasing blood volume, increasing blood pressure. And a lack of ADH causes you to lose a lot of water. Right, now I've talked about this in my pharmacology of drugs class, recreational drugs, how if you drink alcohol, you inhibit the release of antidiuretic hormone, and so you get a dilute urine. And the more you drink, the more fluid you lose, and then you get dehydrated. So this is where that's happening. And it's happening because of these aquaporins that allow water to move out of the urine and back into the body. The juxtaglomerular apparatus. I love anything that's called an apparatus. You know, I love the Golgi apparatus. I mean, any apparatus I'm all about. So juxtaglomerular means adjacent to the glomerulus, as we all know. Isn't it great how you get a Latin lesson for every biology lesson? So there's three parts to the glomerulus: the macula, the extraglomerular mesangial cells, and the juxtaglomerular cells. So the macula is regulating glomerular flow, which means how much blood is going through the glomerulus. And it does this by sensing sodium chloride in the distal tubule. So it sees how much is coming out of the distal tubule, and it decides how much should go into the to the front end of the system. It releases adenosine as a what do you call it? Paracrine hormone. So it's releasing adenosine in the local area, which is going to then cause contraction of the afferent arteriole. So if you contract that afferent arteriole, less blood is going into the glomerulus and you're getting less filtration. So that will decrease your GFR, your glomerular filtration rate. So there's less fluid going into the nephron. Interestingly, caffeine is also a diuretic, because caffeine is an antagonist for the adenosine receptor. So if you block the adenosine receptor, then there's more glomerular filtration, so more fluid going to the glomerulus, and you'll lose more fluid. So that's why caffeine can be a dehydrant. Dehydrant? I think I just made that word up. And this is why if you're one of these bros who drinks vodka and vodka and Red Bull, boy, you're going to get dehydrated the next day, because you're hitting both ends of that nephron and you're really losing a lot of fluid. Okay, extraglomerular mesangial cells then will then contract and restrict the afferent arteriole. So in response to the adenosine, they're contracting, and the arteriole itself contracts, but also these mesangial cells contract, and you're controlling how much blood goes into the glomerulus and how much filtration you get. And then you've got your juxtaglomerular cells, which are really important to us as pharmacologists, because this is where you're going to get your renin release. And this renin is really key to a lot of hypertension control. Okay, so here's our glomerular apparatus, which is just in here, basically. Okay, so here is your afferent arteriole coming in, and I'm getting a little lost. Here's your shoot. Here's your afferent arteriole coming in. Here's your glomerulus, proximal tubule, goes out, goes through the nephron, loop of Henle, comes back around. Here's your distal convoluted tubule on the other side. This whole thing together, I think, is called the nephritic corpuscle or something. Corpuscle is a great word. But anyway, maybe it's capsule. I don't know, let's call it corpuscle. But anyway, here's your glomerular apparatus. So here's the macula densa right on the distal convoluted tubule, so it can sense the sodium and chloride here. Here are the JG cells, and here are the juxtaglomerular cells. The mesangial cells are not noted here, so I'm not really sure. I guess these purple ones are maybe that's smooth muscle of the arteriole. Yeah, I'm not really sure, but they're in there too somewhere. But anyway, here it is, right between the distal convoluted tubule and the afferent and efferent arterioles. And so that's how you control blood flow into the glomerulus and how much fluid is going to be filtered into the nephron. And the key here that for us as pharmacologists is this renin-angiotensin system. So renin is released in response to beta-1 stimulation, SNS. So I don't know if we talked about this last week when we talked about the ANS and the SNS, but another response of the baroreceptor when pressure drops is to stimulate the release of renin here in the juxtaglomerulus. Also, decreased renal perfusion pressure. There's a decreased pressure in the arteriole that causes renin release, and that could be due to a blood pressure drop, which can be caused by dehydration or hemorrhage, right? You've got a large blood volume loss that causes a drop in blood pressure, and so you release renin to try and absorb more water. Decreased sodium in the macula densa. So your macula densa is also controlling this by, if you don't have enough sodium leaving the body, it causes more retention of the sodium. Okay. Mechanism of release. Now this is where I get fancy with my PowerPoint. So, I should have deleted this. Oh well, we're kind of looking at it again. But anyway, sympathetic nervous system, the baroreceptors, sense this drop in blood pressure, or decreased renal blood flow, and that causes release. Okay. So yeah, I didn't need that slide. Mechanism of action. So renin is an enzyme. It goes into the blood, and alpha globulin is a protein that's in the blood. So it's often called angiotensinogen. Remember that suffix there, inogen, means going to produce. Gen means origin of, basically. So angiotensinogen or alpha globulin. So it's going to cleave alpha globulin and produce angiotensin 1. Now, angiotensin 1 doesn't have any effect. It doesn't do anything. It's a decapeptide, 10 amino acids. But this angiotensin 1 then will travel to the lungs. And in the lungs, there's an enzyme called angiotensin converting enzyme. And it's going to cleave 2 amino acids off angiotensin 1 and make angiotensin 2. And now angiotensin 2 is really what we're most concerned with here. Everything else just leads up to it. So we can control angiotensin 2 by controlling the things that lead up to it. Angiotensin 2 effect is going to increase blood pressure. So one thing it can do is bind to the angiotensin 2 receptors, which are on arteries. And kind of as a side note, this is how COVID-19 gets into cells, by AT2 receptors. It binds to the receptor and uses that as a way to attach to cells. And then I don't know how, but at that point, then it gets into the cell through that. So who knows, maybe that would be a good therapy for COVID too. I'm sure they're looking into it. Oops. So angiotensin 2 receptors are G protein coupled receptors. They link to GQ and activate production of IP3 and release of calcium and cause contraction of arteries. So AT2 is directly increasing blood pressure. And it's also going to increase the synthesis and release of aldosterone. Now remember, we talked about aldosterone earlier. Aldosterone is going to increase sodium retention in the distal tubule, distal convoluted tubule. So we've got two things going on here with angiotensin. We are directly contracting arteries, and we're increasing sodium retention, so we're increasing blood volume. And another thing, I don't know if I put on this slide or not, but write this down in your brain somewhere. Angiotensin 2 also causes the release of antidiuretic hormone. So we've got three actions here of angiotensin 2: direct contraction, reabsorption of sodium, and reabsorption of water through release of antidiuretic hormone. Oh, and here we are. So liver is producing your angiotensinogen, and renin comes out of the kidney and converts it to angiotensin 1. Oh, by the way, ACE is in the lungs for whatever reason. Who the hell knows? So the angiotensin converting enzyme is in the lungs, and that converts this to angiotensin 2. Now, what's going to happen to this? It's going to potentiate sympathetic activity, which is something I just learned because I didn't look closely at this figure before. Don't worry about that. Okay, more importantly, tubular reabsorption of sodium and chloride, and that's because of, I should have looked at this figure before aldosterone. Oh, okay, so you're getting a direct reabsorption of sodium, plus you're making aldosterone, which causes a reabsorption of sodium. So, and then we're getting arterial contraction and release of ADH, which is causing water reabsorption. So this is a piece I didn't know about until I just looked at this figure closely. I I still don't know anything about it, so don't worry about it. That's not part of our understanding at this point. Angiotensin 2, though, increases sodium directly, and it releases aldosterone, which is key, and that increases sodium retention and contraction, and then ADH secretion. So basically, whenever you reabsorb sodium into the body, water goes with it automatically. That increases blood volume. But you also have water separately being reabsorbed. So you're increasing blood volume in a couple different ways here. So angiotensin 2 has a strong effect on blood volume. Other blood volume controls, like this is your main blood volume control, but there are other things that can control the volume of the blood. ADH, okay, which we spoke of in a minute ago. But you know, ADH, in addition to being released by angiotensin 2, is directly released by the hypothalamus in response to a decrease in blood volume or increased osmolarity. Okay, so this is separate from the angiotensin-renin system, but also causes reabsorption of water. Oh, there it is, in response to the angiotensin 2. Okay, and ADH then binds to ADH receptors, which are G protein coupled receptors. IP3 calcium causes contraction of arteries. So that's like AT2. It's going to contract all your arteries, bring your blood pressure up. It's also in the collecting ducts, and we talked about this a little bit ago. Causes aquaporins to move into the membrane and increasing water reabsorption. And water is blood volume. Okay, so here's ADH. We're going to start here. We're going to increase osmolarity of the blood, and the hypothalamus notices that. It releases ADH. It also makes you thirsty, so you drink more water. And the ADH then affects the collecting ducts, causes you to reabsorb more water from the collecting ducts, increasing homeostasis, increasing blood volume, decreasing osmolarity. Drinking water, decreasing osmolarity. Okay, so hypothalamus is controlling this based on osmolarity. And it's got two different mechanisms here to bring your osmolarity back down. Other blood volume control. So atrial natriuretic peptide. This is going to do the opposite thing. Natriuretic. Natriuresis means loss of sodium. Nat is sodium, right? Na. Uretic means into the urine. So this is going to be released from atrial cells due to excessive stretch. So when you've got a lot of venous return because your blood volume is so high and you got a lot of pressure, your atria stretch more than normal, they release ANF. And that will cause loss of sodium from the kidneys, from the loops of Henle, and the loss of sodium is in the loops of Henle. And this increases water loss and decreases your blood volume. So ANF is doing the opposite of ADH and aldosterone. ANF is also going to inhibit the release of renin. So you've got a physiological antagonism here between ANP and angiotensin. Sometimes I call it atrial natriuretic factor. It's the same thing. It used to be called factor until they figured out it was a peptide, and then they call it ANP. But I'm an old guy. I forget sometimes that things change. Angiotensin 2 also causes vascular relaxation, cyclic AMP dependent relaxation, and it decreases aldosterone. So we're physiologically antagonizing all of the mechanisms of blood volume increase and vessel contraction here with ANP. Causes relaxation of arteries, GPCR, increases, cyclic GMP, not cyclic AMP. So if you remember, cyclic GMP activates G kinase, which then phosphorylates phospholamban on the ER, increasing calcium back into the thing, and several other mechanisms, which I'm sure you all know, and you would be embarrassed if I reminded you, so I'm not going to go into them. Okay, cardiac distension, sympathetic stimulation. Oh shit, I did it again. There's my hair trigger. Okay, so ANP gets released, BNP2, let's not worry about that. ANP then it's going to inhibit the release of renin. Okay, over here, decreasing renin, which is going to decrease angiotensin and aldosterone. So you're going to get more natriuresis and more diuresis. Blood volume comes down, blood pressure comes down. Okay. And that, my friends, is that. Holy shit, 35 minutes. I'm glad I added a lot more slides yesterday because this would have been a really, really short lecture if I hadn't. But I think that's a good bit of material to digest, I think. I think it would have been longer if I was standing writing all this crap on the board and you're copying it down. I think that's why it takes so long when I'm in class. And I feel uncomfortable sometimes with how fast I'm going over this. But, you know, if you want me to go slower, you're going to have to ask me questions. I'm not really sure how else to do this. Can I see all your faces real quick? You can see mine. Hey, there's Celine. There's Ariana. I get the sense that Ariana is just, she's got like a video and she just plays it every time because she always looks exactly the same. She's in the same place doing the same thing. Mike West is looming over us in the dark. Noemi is here. Hello. Your hair is different, Noemi. Very nice. I like it. He's wit. And Matt Gamellan is shy. Okay. So that's about all I have for today. Yeah, that's it. No questions, comments? Make sure you go over this pretty well. Next week, we're going to get into pathophysiology. I think Tuesday is going to be hypertension. And then Wednesday will probably be coronary artery, Thursday will be coronary artery disease and congestive heart failure. And then the week after on Tuesday, we're going to have a guest lecturer, my friend Perky Gogo, talking about whatever it is he does. And he makes a lot more money than I do. So I'm assuming it's important. Okay, guys, we will see you again next week. Study this weekend. Bye-bye.